Okay, now we're going to talk about the particle on a ring as I trip over the board. So particle on a ring, we've got an electron that's bound to, so it's going to be going in that direction. It's bound to a ring. And I drew this in the center. There is no potential energy whatsoever in the center. So we are constraining the electron to exist as in a circle, so a one-dimensional, or I guess two-dimensional circle around the center point. So one of the things that we need to think about is electron has wave-like properties. And we haven't really imposed that yet with particle in a box. It's kind of hard to do that with vibrational harmonic oscillation, but I want you to think about it. So we're going to turn this on its side. So there's our ring. And if the electron has wave-like properties, that means the wave, let's see if I can do this, must have, boom, oh, awesome, oh, it looks gorgeous. Okay, it means this wave, if I were to cut this, okay, string it out, you would see that when I bring it back together, the wave has to be continuous. If it wasn't continuous, let me find my red marker. If it wasn't continuous, so if I start here and I go around and around and around and around, dang it, I did it again. And around, whoop. So if this doesn't match up, if those two don't match up, what happens is then as it goes around now right here, if we zoom in here, we're going to have destructive interference. Those waves aren't going to be perfectly aligned. There's going to be a slight offset. If there's an offset, there's destructive interference, which means if this thing goes around a couple more times, wave's gone. So that means that there's a condition that has to be set, or met, I should say, that the wavelength here, lambda, is equal to n value or a certain number of wavelengths. So integer value wavelengths, 1 wavelength, 2 wavelengths, 3 wavelengths, has to equal the circumference of the circle. So 2 pi r. So there's a circumference. Has to be integer value wavelength. So I'll write that out. So integer wavelength must equal circumference or destructive interference, which equals bad. Okay, so our electron would annihilate itself based off its wave-like properties if we didn't have this condition met. That's not good. So let's make sure we have this condition met. But, so let's zoom in a little bit more. So n lambda equals 2 pi r, where here's my r. All right. Now this lambda, this is the wavelength of the electron. But we know that light has wavelength equal to c over lambda. But for an electron, we're going to use a de Broglie wavelength. So we've got nh over p or nh over mv, where here we've got de Broglie. Yay. All right. So likewise, this equals 2 pi r. Go team. And so what I'm going to do now is I'm going to relocate this momentum to the right-hand side. So I have nh is equal to 2 pi times mv times r. Again, remember, this is our momentum. This is p. The cool thing about this is anytime you have the value times r, it becomes the angular value. Well, that's not true. So you have angular momentum if you have p times r. It's angular velocity if you have v times r. Where r is your radius to some sort of circle. And so this right here is our angular momentum. Angular momentum. Cool? Is everyone following? Like I would hear you if you pause and rewind if it's not. Okay, I think I've said that joke way too many times. I do apologize. So angular momentum is equal to, times 2 pi is equal to nh. Well, I'm going to move this 2 pi, so I get nh over 2 pi. There's h bar equals nh bar equals mvr, or my angular momentum. And I'm going to rewrite my angular momentum. I'm going to take this up here. So I've got nh bar is equal to mvr, which is equal to j sub z. jz. Back 10, 15 years ago, that wasn't as funny of a joke. Anyway, so this is the z component of the momentum, of the angular momentum. Oh, there we go. Okay, now in Atkins on page 282, this is the chemist's toolkit. There we go. The chemist's toolkit number 20, it talks about the angular momentum, and it talks about how you have 3 components of the angular momentum, both in the x direction, the y direction, and the z direction. We only care about the z direction for the reason of the way that I've set up my coordinate system here. So my z direction is going to be coming out of the board. So the electron's going this way via right-hand rule. Electron has a direction and it curves. So speed, angle, this is the direction, and so this is the z direction of my angular momentum. Or if I were looking at this piece, it would be in the up direction. Okay. All right, so we've, oh goodness, decline. Sorry about that. Okay, so we've got j sub z, the z direction or z component of the angular momentum is equal to nh bar. Holy crap, that's quantized. Integer value n times h bar. Problem though, even though our angular momentum is quantized, tip of the hat to the Bohr model, we've already used n for the energy state of our particle in a box. So we kind of, and this is angular momentum. This is an energy state. This is angular momentum. So we need a different quantum number to define how this quantization occurs. And this is where we're going to introduce, so need new quantum number. N is taken. Okay, so I'm going to introduce j sub z is equal to m sub l h bar. Here's m sub l. Yes, I have bypassed. We'll get back to L. Particle in a ring, we're just going to bypass L. We're going to go straight to m sub l. Okay, so we know that our j sub z, angular momentum in the z direction, m sub l h bar, where this is our quantum number. So m sub l is our angular momentum. Quantum number in the z direction. Okay. The other thing is that we have some restrictions on what m sub l can be, and we'll get back to what these things mean as we add more tools into our toolkit. But m sub l can equal 0, plus or minus 1, plus or minus 2, and so on. It could be plus or minus 40. I doubt you'll get that high, but it could be. Okay. Other thing. If m sub l is less than 0, so you notice how you have these negative signs here, that means you have counterclockwise direction. Like everything in life, physical chemistry can explain it. No. So anytime you have anything negative or a sign change in pchem, you're going to have some sort of indication of direction. Positive heat flow means it's heat going out of the system. Oh my God, so sorry. Positive energy means heat coming into the system. Negative energy means it's going out of the system. Likewise, if you have a positive value here in m sub l, that means it's going in the clockwise direction. And if it's negative, it's going in the counterclockwise direction. All right. Cool. So angular momentum is quantized for the particle in a ring system. But let's go back to what we're trying to do with all these quantum systems. We want to answer 2 questions. Where are the electrons and what is their energy? Notice I haven't answered either of those questions. I've just told you that, or I've shown you that angular momentum is quantized based on the condition that the electron bound to a ring, which has wave-like properties, is going to have to adhere to the condition that the integer wavelength is going to have to equal the circumference. Well, how do I find the energy and where do I find the electron? Well, we will need 2 things to do that. we will need the wave function. So psi of x equals what? And from there, we're going to have, okay, well, what's the Hamiltonian operating on the wave function to give us our energy? Well, what wave function describes the electron bound to a ring? I will tell you. We're going to bypass trying to guess what these things are anymore, and I'm just going to give you the answer. So instead of having psi as a function of x, we're leaving Cartesian coordinates and we're moving into spherical coordinates. So my angle is going to be phi, and this is going to be e to the I m sub l phi divided by 2 pi 1/2. Okay, so this is the normalized wave function. Here's my normalization constant, and I can rewrite this 1 over 2 pi, radical that, e to the I m sub l phi. Okay, so here's my normalization constant. This is normalized to the electron having 100% probability of existing on this ring, e to the I m sub l phi. Now, I know I said we weren't going to be doing many complex values in our wave functions. I'm so sorry, I kind of lied. I just didn't. We are. Go team. Hopefully it's not as scary. So you've got now a quantum number inside the wave function. Cool. We take this, we put it in to the Schrodinger equation. We operate on this with the Hamiltonian. Apply the boundary conditions, which the boundary conditions, one of which being the wavelength of this wave function has to, or the wave function has to exist in this circular environment. We do that, and we get the energy equals, I can never remember this one, J sub z, again, that's our angular momentum, over 2I. I'll tell you what these things are in a little bit. But we know that J sub z is m sub l h bar. And so this, oops, I think this should be squared. There we go. So m sub l squared, h bar squared over 2I. So I here is called our moment of inertia. And it is going to equal, well, it equals many things. But for the simplest system, it's going to equal the mass times r squared. So this r is going to be, again, the same radiance as we've been working with. The other thing that I want to note is that the moment of inertia is going to change depending on what your system might look like. For a particle on a ring, very simple, m r squared. If you happen to, when we get into rotational spectroscopy, which is very soon, you're going to see that the shape of the object. So like this, who we have, this is propanol. So propanol is going to have a different type of moment of inertia than, say, ethane. Okay, and so you'd have to take into account the planes of rotation or the axes of rotation depending on the shape of your molecule. All right. Other thing I want to say is, if I wanted to know some information about the angular momentum, I also have an angular momentum operator that would yield the angular momentum observable. And in the z direction, because again, we have angular momentum in the x, the y, and the z direction, the angular momentum operator is L hat sub z, and this is for the z direction. And I have that is equals to h bar over I d phi. And so much like the momentum operator, you have minus I h bar, which is the same thing as h bar over I d dx. So now we have the angular momentum operator is, you can also see this is minus I h bar d phi. So you're asking the question of what's the change as you change this angle. So what's the derivative of the wave function as you change this angle multiplied by a minus IH bar? Okay, I think that's all I want to say here. But we're building and building towards what happens when the electron is bound only from, excuse me, the interaction with the proton, which would be the hydrogen atom. And so using these models to ask the question, where's the electron and what is their energy? From that, we need a wave function. Where is it? Such that we can square it and find its probability. What is its energy? Or what does the Hamiltonian tell us? So to answer those two questions, we need to know what wave function. But in order to know what wave function, we need to know what boundary conditions we have. And those boundary conditions are based on how we set up our system and what our potential energy interaction is. Okay, so here's the two-dimensional answer. There's our wave function, depends on phi. There's our energy, ml squared, h bar squared over 2i, I, moment of inertia. Cool. All right, we're going to complicate the hell out of it by putting this thing in 3 dimensions. Go team.